Now we live in a world where everything is not nice and neat and everything is a right triangle, and we're able to solve all the applications with a right triangle. There's applications where we need to solve triangles or work with triangles that are not right, but rather oblique triangles. Oblique triangles basically come in two shapes. One where all the interior angles are less than 90 degrees, or one where two are less than 90 degrees, but one is an obtuse angle, an angle that's greater than 90 but less than 180. So what can we do to solve these types of triangles? How can trigonometry help us move forward when we have to work with triangles such as these? Unfortunately, trigonometry can't help. So let me walk through an idea with you and get to this idea called the law of sines. The law of sines is basically developed such as this. Let's imagine I have this triangle, for example, and I'm going to draw an altitude within it. I'm going to label that an H. All right. Then what I'm going to do is I'm going to look at the sine of A equals my opposite over my hypotenuse. So that equals H over B. Sorry, bad H right there. Likewise, I'm going to look at this B angle over here, and the sine of B equals the opposite over the hypotenuse, and the opposite is H over an A. All right, let's manipulate those around a little bit. So the top one, I'm going to rewrite the top one as H equals the sine of A times B. And the second one I'm going to write as H equals the sine of B times A. Now I have two equations, both set equal to H, so I can then set the sine of A times B equals the sine of B times an A. Basically, I was able to set both of those together. From here, I'm going to divide both sides through by sine A, sine B, and I'll help you understand here why and a little bit why I chose to do that. And this is valid because whatever I do to one side, I can do to the other, right? Doing that, I have a sine A factors out with a sine A on the denominator, and on the right side, a sine B factors out a sine B. And then what I'm left with is I'm left with a fascinating relationship. I'm left with this idea that B over the sine of B equals A over the sine of A. And that's the first part of our law of sines, where that if I can find a side and its angle, its corresponding angle, and another side, I could find out some more parts of that particular triangle. Now I can extend this one step further too. If I just repeat the step again, but rather than looking for angle B, but angle C, I can complete the law of sines by saying B, or the ratio of B to its angle equals A to its angle. The ratio of its angle equals C, or ratio of C to its angle. And so what we have here is a very useful tool called the law of sines. So let's look at an example here in a little bit. I'll clean my board up as we kind of look at a cool application. So let's solve our first oblique triangle. Now, there's two types of oblique triangles, or two types of information that we'll have that allows us to solve an oblique triangle through the law of sines. Or they both include where we know one side and two angles. So I have an SAA. If we have a triangle where I know a side and then an angle and then the next angle, kind of as I go around the triangle, I know a side, an angle, then an angle, I can use the law of sines. And likewise, we'll see an example where I have an angle, side, and an angle. I'm able to work with that. So what can we do? How do we solve this oblique triangle? Well, first thing I might want to do is look for the angle of B. I know the interior angles add up to 180 degrees. So I know then that 63 plus 46 plus x equals 180 degrees, or 180. So adding all those up, that's what, 109 plus x equals 180. X equals 71. All right, well, I guess I could have used B since that was the angle there. So I can put a 71 in there. All right, we're well on our way now. All right, now let's use the law of sines where I have my side C and an angle C, and I have an angle A. So A over sine of A equals C over sine of C. So let's use that relationship. So A over the sine of A equals C over the sine of C. The value I do not know at that particular case. What am I solving for? I don't know A, so I'm going to solve that for A. So that's A equals the sine of A times C over the sine of C. All right, my values then, so this is A equals the sine of A, which is 46 degrees, times my value of C, which is 56 inches, all over the sine of C, which is 63 degrees. All right, none of those are nice exact angles that I'm familiar with, so I'm going to use my black box. Sine of 46 degrees times 56 divided by the sine of 63. And that equals 45.2, or roughly, yeah, I'll go approximately 45.2. So my angle, or my side of A, is 45.2 approximately in inches. All right, now I want to find the side of B, and I can use a relationship, anything that works here. So I have all the angles, and however, I'm going to use my side C rather than my side A. Side A is an approximation, so I'm going to use the relationship between B and C. So that will be B over the sine of B equals C over the sine of C. Values I know. I don't know B. That's what I'm solving for. So I'm going to multiply both sides by the sine of B. Plug in values. Sine of B. Sine is 71 degrees. So the sine of 71 degrees times my value C times the 56 divided by the sine of C, which is 63 degrees. Again, use a black box. $59.4 approximately inches. And so my other side is 59.4 inches. And I'm going to see if that looks reasonable. The side opposite my 71, since 71 is my greatest angle, I would expect the side opposite that to be my greatest length. 46 is my smallest angle, so I would expect the side opposite that to be my smallest value. And I can see that all those things match up and appear to be reasonable. So we just solved our first non-right triangle, or an oblique triangle, by using the law of sines. Our next example is an angle side angle triangle, meaning that I know an angle, its inclusive side, and the angle right next to that. And so we call that an ASA, or an angle side angle oblique triangle. With that means that we can use the law of sines to solve the triangle. So let's begin with the easy part first, which is the interior angles. I know the interior angles add up to 180 degrees. So that being the case, then I would have 50 plus 33.5 plus B this time equals 180, 88.5. And B equals, subtract 88.5 from both sides, gives me a 91.5. All right, so 91.5 degrees. So it's not quite a right triangle, which again is by definition, makes it an oblique triangle. So that value is 91.5 degrees. From there, let's start seeing what law of sines are useful. I know both B and the side opposite to B, so it looks like that's going to be my baseline for both of these. So one is going to be an A over the sine of A equals B over the sine of B. And I'm doing that one. I'm going to solve for what I don't know. I don't know A, so I'm going to solve for A. So I'll just rewrite it as A equals, I'll do B first this time. It doesn't matter. B times the sine of A over the sine of B. And before I get the black box out, I know that my other relationship also will be C over the sine of C equals B over the sine of B. Again, I'm using the ratio of the B's because I know both values. I want to solve for the C. So that equals C times B sine of C over the sine of B. So I did a little bit of algebra to manipulate those two trigonometric equations around the law of sines. So now I can have them both solved for A and C. Notice that I'm using known values and not an approximation. I'm not finding what A is, then use that ratio with the A's. Rather, I'm using values that are exact values right now. And if we don't do that, that could be a reason why sometimes our solutions might be off by a little bit, is we're using an approximation within our question, and an approximation will compound itself and gain further error. All right, so what are my values? Let's just do this one first. C equals B, 76, times the sine of C. C is 33.5. All over the sine of B, which is 95. So the sine of B, which is 91.5. All right, let's put that in the black box. 76 times sine 33.5 divided by sine 91.5 equals approximately 41.96. I'm going to have to make that approximately 42 then. And it's approximation, so I'm going to have to live with that. Notice again, I'm not going to use this approximation to solve the other answer. That's why I'm going with the ratios of A and the ratios of B. So A equals B, which was a 76. Confirm, 76. Times the sine of A. A is a value that's not an approximation. It was given over the sine of B. And the sine of B, 91.5. That is not an approximation. That was something we discovered, but it was an exact answer, not an approximation. Solve that. 76 times sine of 50 divided by sine of 91.5. Bummer, I typed it in wrong. 76 times sine 50 divided by sine 91.5. And approximately 48.2 or 58.2. And those were inches. Whoops, not 42 degrees, Willie. That's the side. That's inches. So I was able to solve the triangle. A is 58.2 approximately, and C is approximately 42. And again, does that make sense based on our angles? My smallest angle is 33.5, so I would expect that to extend to the shortest side. 42 inches is the shortest side. B is my greatest angle, and that extends to the largest side, which is 76. And so those answers, results do seem reasonable, so that gives me some confidence I did not make a mistake along the way. All right.